Today we'll be working on the following problem. Let D be a dense set in R and mu be a positive measure defined on Borel sets of R. And then suppose that for any x sub 0 in D, A less than B in R, the interval shift translated by x sub 0, the measure is the same as the original interval. And then we want to show that actually the measure of interval AB is lambda times B minus A, where lambda is the measure on the unit interval. So pause the video if you work on this problem by yourself. Okay, let's prove this. So here we just want to use some basic properties of the positive measure. Basically, it's it's between 0 to infinity, and then it defined on the Borel set. The Borel set is the smallest sigma algebra generated by the open sets in R. And now here we only assume like this is a translation invariant for some points in D. In fact, we are going to prove that such mu actually has the translation invariant for any x. So by assumption, basically, we assumption meaning like we know this, right? Plus x0 to b plus x0. This close, open. The measure is the same as A, B, because this is just the translated by x sub 0. So first, we want to see not a surprise, like any single point has measure 0. We want to show that. And the reason being is what? Because D is dense. So this open interval with D intersects D is not empty for ON, right? So meaning like now we can find x sub n in this interval. X sub n is in D. And now if you look at this from A to A plus 1, let's see. And now we divided it by x sub n. So x sub n, A plus 2x sub n to A plus n x sub n, right? Because n x sub n is less than 1. So we can make sure this A plus n sub n is less or equal than A sub I. Now if we see the measure, and then each of this interval has exactly the same measure because of the translation by x sub n. So when you add them together, you have this which means like n times the measure from A to A plus x sub n is less or equal than the total from A to A sub 1, the total measure, right? Because this n parts, and each of them are the same as this, translated by x sub n. And then if you, from here, we know 0 is less or equal than the measure of this single point, and then less or equal than this one, right? Because A is in the interval of this, which is less or equal than 1 over n from A to A plus 1. And then this goes to 0 as n goes to infinity. And this proves like the measure of the singular point must be 0, right? Now we can prove actually, even though the assumption is translation invariant for a point only in D, but we can prove this holds for any point. So this interval, the measure is the same as the original one. So again, same, D is dense. So we can find a sequence in D, and we can make this sequence decreasingly approach to X. And now if you look at this interval from A plus X, B plus X, and then we can make A plus X sub n in between, and this is B plus X sub n, right? So when n is large enough, so now we want to calculate the measure of this two interval. So we have this relationship, right? So if you want to come from A plus X to B plus X, this is actually, I first, I take the measure from A plus X sub n to B plus sub n, X sub n. And then I have to minus this part. So mu from B plus X to B plus X sub n. And now I have this measure, and then I add back this A plus X to A plus Xn, right? This holds for On. Now this one is mu of AB, right? It's translated by X sub n. And then this goes to, let n goes to infinity. This will be mu AB interval minus, this goes to any single point, B sub X, right? B sub X in this interval, and then plus, and also the same, A plus X, this single point. It contained in all the subintervals. So if you go to, let n goes to infinity, this is exactly mu AB, right? Because as from 1, the measure of a single point is 0. So now we're ready to prove for O A less than B. This actually is lambda times B minus A, where lambda is the measure of unit interval, right? So from translation, all we need to show is, because this is, if you translate it by A, because we already proved by any translation X, right? So if you translate by A, you have B minus A. These are equal, right? So you want to show this is actually lambda times B minus A. So this now is a very typical, because typical approach technique, like we're going to do this. We first prove, so basically you want to show for any R, this equal to lambda times R, right? For any R. If we can show this, then we prove the main result. So we first prove when R is actually rational number, this holds, right? So let's see, if you do that, we want to prove, calculate basically n over m. We want to see this one. We want to prove that is actually lambda times n over m, for any nm is a integer, right? So again, the same if you look at this from 0, this n over m, n over 2n over m, and then all the way to m times n over m, right? This is actually, so we have, and then each this subinterval, they all have the same measure because they all shift by n over m, right? So then we have how many of them? M of them. So m times this measure n over m is equal to, when you add them together, it's actually the measure from 0 to n, right? So now if you look at from 0 to n, and then you can have divided into this part, the interval of each of this are the same as the measure of the unit interval, right? So this actually is n times the measure from 0 to 1, which is n lambda, right? So you divide it by m by both sides, then we have, so what we proved is that if any q in q, and then the measure from 0 to q, this interval is actually q times lambda, right? So we proved that this holds for any rational numbers. And now the typical approach is like for any r in this, we can find a rational numbers approach to goes to r, and then we can even make it increasingly, goes to r, increasingly goes to r, right? And because all the rational numbers are dense in r. And now in this case, we know this r, because now if you look at the the interval from 0 to qn, and then this is, we make qn increasingly goes to r, so this goes to 0 to r, right? And now because the mu is the measure, so we know this is actually the limit when n goes to infinity from 0 to q sub n, right? Because of this, it's increasing. So, and now the limit n goes to infinity. We know, we already proved like the measure of this is actually qn times lambda, and now qn also goes to r, and then this is r times lambda. So that's it.